Any questions about anything? How everybody doing? We survived the midterm. People did pretty well. That was good. With last class, we were having a hard time understanding the one reduction. So we'll do another reduction. So this one is more general and more subtle in some ways. It generalizes what we did before. All right, so we already know that the halting problem is undecidable, and we want to prove that the following class of problems is undecidable. If you give me a Turing machine and you want to know something about the language of that Turing machine, you want to know something about which inputs it says yes halts on and which inputs it doesn't halt on, then it seems reasonable that that would be undecidable, as opposed to knowing, if you just ask, well, how many states does it have, or something semantic about the Turing machine. That's clearly might not be hard, but knowing something about what the Turing machine does is undecidable. So there's something called Rice's theorem that you should all know, and it states, suppose there's a computational problem that takes as input a Turing machine, and you look at the language of the Turing machine, and you want that language to have some property. All right, it's a property of the set of inputs that the Turing machine accepts. I think one of the problems that we were having last class is people are not differentiating between an individual string having, say, the 0 to the n, 1 to the n property versus the entire language having that property, right? Versus a Turing machine having the property that its language has that property, right? So the example that clearly we're going to give here is the one we did last class, which was given a Turing machine, the language, the set of inputs on which the Turing machine halts happens to be a regular language, all right? So that was the example we were doing. Now, what do we want to conclude? So that's just stating again that this states what the Turing machine does on each input, not how it does it. So from that statement, we want to conclude that the problem is undecidable. Now, there's a little gap you see there, and it's because we need to give space for what happens if P always said yes or always said no. Then in some ways that's a property of the language, but it's clearly decidable. If P is always a yes or always a no, then clearly that's decidable. But this is saying if we know that P sometimes says yes and sometimes says no, but not always does one or the other, then the problem is undecidable. All right? Yes?
Could you give, so P is that you have a machine M, and the language of that machine M is said to be regular.
In this example, yes.
In this example, and you're saying that problem P is undecidable.
Yes.
Could you go over what the term undecidable means again?
Yes. Undecidable means that a problem is undecidable if a problem is decidable if there's a Turing machine that on every input halts and gives the right answer.
Yes, correct.
Right? So a problem is undecidable if every Turing machine fails on some input.
So you've got this magic input that you could feed it to any Turing machine and it would fail. Is that what the last sentence means?
No.
No? Okay.
No, undecidable.
Because you said that there is one input for which all Turing machines fail, correct?
No, I definitely didn't say that. Okay. So a problem is decidable, right? We say P decidable if there exists a Turing machine that says for all inputs, what the Turing machine does on that input is what the problem wants it to do, right? And it halts. It's always halting. So the deciding means the Turing machine always halts with yes or no with the correct answer, right? So undecidable means that for all Turing machines, there exists an input such that what the Turing machine does on that input is different than what it requires.
Yes, okay.
Right? And you're kind of implying that there was one input that was bad for every Turing machine. And that's not the case. Every Turing machine could have a different
Input.
could have, right? In fact, if you might remember the assignment, we were trying to prove that there was some problem that was undecidable. And every Turing machine had a nemesis input. Right? That was the F of M. Or that was the input was itself. That was anyway, so we know that this is undecidable. We know that there's no algorithm that always halts and says yes on it. So we want to prove that this is undecidable. That no algorithm can always can halt and decide whether some M is in P or not. All right? So everybody understand what we're doing so far?
Can you explain the Rice theorem one more time?
Yeah. Yeah, so Rice's theorem. Oops. I have too many things in my pocket. I guess I stuck the mic in there. But now my pocket's too full. All right, so what we're trying to say is let P be a computational problem. All right, and the input that the problem takes is a Turing machine. And then the answer is either says something about the language of that Turing machine. What's the language of the Turing machine? It's this. We look at the set of inputs to M for which M says yes. Right? Halton says yes. So L of M is the set of inputs, set of I's for which M on I Halton says yes. Right? And we want to, and then there's some property about that set. Right? The property might be that the language is regular. Right? It could be some other property. Right? So that's all we know about P, is that it has this form. Well, actually, we also know that P doesn't say yes on everything and doesn't say no on everything. Right? Does that make sense? And from that, we can prove that P doesn't have an algorithm that halts and says yes on everything. Yes?
Does that property would have, like whatever property you said, have any effect on P being undecidable?
No, because I just said no matter what the property is, it will be undecidable.
So you didn't need to write that, like that line.
What line? This line? Do I have to write it?
Yeah, you never need to write it if it doesn't affect anything.
It's whatever property I plug in here. I can plug in any property whatsoever. And
So don't need to write that property if that property doesn't change.
it changes the problem. It changes what the problem is. But I'm saying any problem of this form is undecidable. So this is a huge class of problems, right? For every property of the language, this problem is undecidable. Everybody got that? So the proof is going to be, it uncovers this proof that we spent a long time on, so you might think it's going to be really hard. But it's basically the same proof that we did here. All right, with just a little tweaks on it. All right? So one thing we want to note is that if you have two Turing machines, two possible inputs to P, and their languages are exactly the same, right, then the answer for M is the same as the answer for P, for M prime. Right? If M is a yes to P, then M prime is a yes. If M's a no, why is that? Because this language here either has the property or it doesn't. Right? Everybody got that? So you might remember we had that kind of idea in this proof here. We're going to be talking about, we're going to have Turing machines that have the same language, and then hence they have the same answer. All right, so our goal now is to find some nice Turing machine that has the very, here, let's consider this Turing machine here. This is the empty Turing machine, and what it does is it says no. All right, all it does is it halts and says no. So what's the language of this Turing machine? It's empty. It's the empty language. All right. So if you give this empty Turing machine to P, it could either say yes or no. Right? But at this moment, there's sort of symmetry between yeses and nos, and we're going to just assume that P says no on this Turing machine. If it happens to say yes, the proof could be different. If we just switch the proof around, it's about the same.
Is that because P is not equal to nothing?
No, these are different issues. This is saying there are Turing machines in which the P says yes to, right? They're sort of different levels. This Turing machine is a Turing machine that says no to everything. So this Turing machine's language is nothing, right? But P could say anything on this Turing machine. It could say yes or no. But I'm just sort of claiming that the proof is pretty much symmetric if we switched it, and we might as well just assume one case. So I'm going to just assume that the Turing machine, that P says no to this Turing machine. It's just one example of a Turing machine. We know it says no to something, and this is one thing that it says no to. But now we're going to use this property up here that P says yes to something. There's some Turing machine that it says yes to. All right? So let M yes be a Turing machine that P says yes to. All right? So what do we know so far? We have a Turing machine P empty that says no to everything, and it happens that P says no to it. And then there's another Turing machine, P yes. We don't know anything about what it says yes and no to, right? We don't know anything about its language. All we know about it is that P says yes to it. All right? So now, yes?
Can you go back to the last slide? Can you prove this by using logic rule to turn everything into an OR statement?
Let's not look for other proofs until I finish the proof I've got. All right, so we're doing the usual reduction, right? We're going to assume that we have an oracle for P. We have this is a flaming bush where you give it a Turing machine and it tells you whether the language of that Turing machine has the given property or not, right? And our goal is to come up with a Turing machine for the halting problem. All right, so we're given as input, what's our input is an M and an I. And we want to know, does this M halt on this I? Right? So what do we have to do? I'm this algorithm here. I'm given an M and the I, and I want to run this oracle. Right? In order to run this oracle, I have to give this oracle some Turing machine M prime. Right? So I'm going to design an M prime here, and we'll see what that M prime is. So here's the M prime. Right? What M prime does on its input is it first, as often, ignores its input. All it does is it runs M on I. right? That's what it starts by doing, is runs in M on I. And then after running, if M on I, well, of course, if M on I runs forever, then M prime runs forever, right? And if M on I halts, then what we do is we take our input, our I prime input, and we run M yes on it. Remember, there's this program in yes. We don't know what it does. It sometimes yes, answers yes, sometimes it answers no, sometimes it runs forever. We don't know what it does, right? But we just run I prime on it. And then whatever the MES program says, we say.
MES holds.
What?
MES holds, always.
M?
Yes, MES, the program MES always holds.
No, we don't know anything about MES. MES sometimes halts, sometimes doesn't halt. When it halts, it sometimes accepts, sometimes rejects. We don't know anything about what it does.
So how we differentiate the case where M and I hold, does not hold, and MES and I prime.
Well, why don't we wait for the proof? All right, so as always, if the oracle says yes, we say yes. If the oracle says no, we say no. Right? So now we have to prove that this algorithm works. All right? So let's look at the two cases. The one case is that M halts on I. Right? Well, let's see what happens when M halts on I. This is, I think we're going to see what you're going to do. If M halts on I, then this line really isn't doing anything. Right? What we're really doing is we're just running M yes on our input. Right? So what's the language? We want to know the language of M prime. Right? Because whether P says yes or not depends on the language of its input. We're giving P, the P oracle, M prime, and so we want to know what is the language of M prime. Right? And, well, what we can notice is the language of M prime is the same as the language of M yes. Right? We don't know anything about what M yes does, whether it halts or doesn't halt, says yes, says no. But whatever it does, M prime does the same thing. Right? So the set of inputs on which this machine halts and says yes is the same for the two machines. Right? Everybody see that these two machines have the same language? Yeah? All right. So what are we going to do from that? Well, remember we assumed that P yes was a yes to P, that M yes here, we assume, what do we know about M yes, is that P says yes to it. That the language of M yes has the property so that P says yes. Well, if these two machines have the same languages, then their answers to P has to be the same. Right? So if M yes is a yes, then our M prime is a yes. Right? And if our M prime is a yes, what's the oracle going to say? The oracle is going to say yes. So there comes the yes from our oracle, which gives us a yes. And that's great, because when M halts on I, what are we supposed to say? We're supposed to say yes. Right? Everybody got that?
What does the step run M and I is used for?
It's for the next line. Wait for the proof. All right, so now let's look at the other case. Now let's suppose M runs forever on I. Right? In this case, we're supposed to say no. So let's see what M prime does. We construct this M prime, and what does M prime do? Well, it runs M on I and runs forever. Right? It doesn't matter what our input is. No matter what our input is, this thing runs forever. So what's the language of M prime? It's the empty language, right? Yeah?
Okay, so when you said M runs forever, what does M prime do?
M prime is what M prime is doing is it's running M on I.
Okay, got it.
So if m runs forever on I, then m prime runs forever on I prime. So whatever I prime is, m prime is basically saying no, right? It's not saying no, it's running forever, which means that it's not in its language.
So it doesn't really matter about the input then?
Yeah, no matter what the input is, it runs forever. And so what does m prime accept? It accepts nothing.
Nothing, right?
Right? So, and remember m empty, what its language was. It was also the empty language, right? So their languages are the same. Welcome, you're missing a great proof. All right, so everybody see that these languages are the same? All right, so what do we know about m empty? Remember at the beginning we assumed that that m empty was not in P. That P says no to m empty. Right? So if these languages are the same, then that means that m prime is also a node in P. Right? Because they have the same languages, so they either both have the property P requires or both don't have the property. So since P empty is a node of P, m prime is a node of P. Right? So what does our oracle say? Our oracle says no, and hence we say no, and we're very happy. Everybody get that? That's it for the Rice's theorem.
Can you please just again differentiate between yes am I and yes am I?
All right. You know, one of the problems, I feel your pain, because one of the problems with all these Turing machines, all these proofs, is there's so many Turing machines being thrown around, right? And there's so many, there's inputs, and there's sets of inputs, and their language, a language is a set of inputs, and there's Turing machines. So let's identify all the Turing machines here, right? The oracle is kind of like a Turing machine. It solves P for us, right? It's an algorithm, right? So that's one algorithm. And we're designing another algorithm here, which is supposed to be designing the halting problem, right? And what is the input to the halting problem? The input to the halting problem is the description of a Turing machine and an input for it, right? So what is M? M is the description of that Turing machine, right? What is M prime? M prime, we do an instance map from our M to the M prime, right? So the M prime is what we're feeding this oracle, right? So our oracle is being fed M and I. This oracle is being fed M prime. Now, you might ask, well, what about P empty and P yes? What are they? Well, there's just some Turing machines that we came up with. This P empty Turing machine, we know exactly what it is. It's the Turing machine that just always says no, right? And what do we know about P empty? We know it always says no, so that its language is nothing. It's the empty set. And we know that P says no to it, right? And P yes, it's some other generic Turing machine. And what do we know about it? The only thing we know about it is that P says yes to it, right? So how many algorithms are there? There's 1, 2, 3, 4, 5, 6. 6 algorithms in this proof. All right? And, you know, for me, I can kind of go over this proof in my sleep because, well, I've been teaching this for 20 years. And when I made it the slides was the first time I was teaching it, and I just knew it. I just typed in the slides, right? So I don't know. I must have learned this in some class or other, but I don't remember even learning it. So if it's the first time you've seen it, right, then I appreciate this stuff is tricky because, as we see, there's 6 algorithms. There's the oracle that solves P.
Right, so the 2 oracles.
Well, that's the two oracles. So the oracle that solves the halting problem. There's the Turing machine that's the input to the halting problem, and the Turing machine that's the input to the oracle. There's the M yes that we know P says yes to, and there's the M no that we know P says no to. 6. Yes.
Can you number the algorithms in your slides? So
Absolutely not. Absolutely not, because the numbers 1 through 6 would be completely meaningless to anybody other than me who gave them a random order. I think they have reasonably good names. Next question.
I think I already asked you this question, but I asked you if the bottom line of every undecidable problem was a halting problem.
The bottom line?
Yeah, I mean, is every undecidable problem is reducible
To the halting problem.
yes, because the only reduction we've done so far with
No, they're going to be harder and harder problems. You could spend your whole life studying this, hierarchies of undecidable problems. And we're going to look at other ones. And yeah.
I leave that to you.
We're- exactly. Now, other than teaching 2001, do you know how many times I'm teaching 2001 this term?
4 times.
3 times.
This term?
Twice this term, right? I do it in the morning, and I do it now, and I do it next term. So I'm Mr. 2001 this term. All sections of 2001, you have to pass through me. Yes?
The other case, M doesn't halt.
M doesn't halt. Yes, let's do that case again.
Language M prime is nothing. But how does it know? It keeps having M prime.
How does what know?
The other oracle.
This oracle?
Yeah.
This oracle is a magical oracle. You give it an M prime, and it'll tell you M prime is in P or is it not in P.
But it will try on all inputs, right?
We don't want to micromanage our oracles. You know, you go up to God and you say, God, how do you know your answers? She's going to be pissed. All right, so we don't want to micromanage her. So that's why we call it an oracle as opposed, people might ask, what's the difference between a Turing machine and an oracle? Is an oracle is sort of magic black box. You put in the answer comes out.
You have to know why the answers.
No, you don't.
No, you don't. It's not for us to question why. We're just saying if we had an oracle for this, then we'd have an oracle for this.
Get that. But when you're saying that M prime is language of nothing,
Yes.
that means the other oracle is running on all inputs and can't find anything that works, so more or less.
It is true that
Since,
M prime is running forever on every input.
well, how is it getting to the second input when it's running for the first input? Like how
But-
do you know?
Now let's back up a minute. It seems to me that you're arguing that knowing whether M prime is in P or not seems like an undecidable problem. Is that what you're arguing? Well, that's a good thing to argue because that's what we're trying to prove. Right? The whole point of this is to prove that this problem is undecidable, that there is no such oracle. Right? We say, is there a magical oracle like this? Is there an algorithm like this? No. Why? Because if there was, then there'd be an oracle for the halting problem, which we already know is undecidable.
It's saying that the first action of the M prime algorithm isn't, in some cases, it will never end.
Yes.
How are we supposed to do the next action if the first one never ends?
Well, if M, you're absolutely right. Well, nobody's running M prime, by the way.
It would run forever.
Yeah, nobody's running M prime.
No, but run M and I sometimes doesn't stop, so how do we do next actions?
Yeah, but who's we? I'm not running M prime. Right? M prime is this Turing machine. We give it to the oracle, and I don't know what the oracle does. The oracle is magic. It either says it has property P or it doesn't. Right? So yes, the whole point of this is that it's hard to know anything about what... The whole point is we don't know what M prime does because we don't know what M does. And that's the whole point is if he could tell us what M prime does, then we would have some sense of what M does, right? But we don't know how to know what M does, so we don't know what M prime does. So the oracle can't answer the P question. Yes?
Is the oracle similar to Schrodinger's box?
No, the cat is either dead or alive. It has nothing to do with Schrodinger's cat. All right, that's quantum mechanics, which is not this course. All right, any other questions? I need you at my house today. I'm trying to undo a tap, and my son and I can't undo the tap. Exactly. All right. How are we good doing with Rice's theorem? All right. I try to always answer the question for people, what should you know about Rice's theorem for the exam? All right. It's always a good question. Right, so I would say a reasonable question is, I give you a problem like, here's problem P. It takes as input a Turing machine, and it asks whether the language of the Turing machine, whether the Turing machine, right here, let's write something down, because you won't follow what I'm saying anyway. So suppose on a test I say, here's a problem. You're given an input as a Turing machine, and you say M on I halts if and only if I is even. All right? So I might ask you to prove that this is undecidable. Right? And I'll tell you specifically whether or not you're allowed to use Rice's theorem, or maybe I'll say, if you can use Rice's theorem, use Rice's theorem. Right? So you look at this, what is this asking? This is asking whether the language of M is inputs which are even. Right? So does Rice's theorem apply to this? Yes, right? Why does Rice's theorem apply? Why? Because P is defined to be some property of the language of M, right? And P says yes to some Turing machines and says no to some Turing machines, right? So you can just say, by Rice's theorem, P is undecidable. Well, if the question, well, you might have to say why. You have to know what is Rice's theorem, right? I might say, can you use Rice's theorem? And if so, why? You have to say, well, this problem is only talking about the language of the machine, right? And it doesn't always, P isn't always yes and P isn't always no, right? And hence P is undecidable. So you should know the statement of Rice's theorem, and it's probably good to know the proof of Rice's theorem, because I might give you another problem that Rice's theorem doesn't quite work on, and then you can't use Rice's theorem. But it's a nice proof technique, and you can just sort of change the proof technique. Or maybe, who knows, maybe I'll even ask you in the test, give me the proof of Rice's theorem. All right? I think it's a reasonable, it's one of the core theorems that's covered in this course, and I think you should know it. Any questions about it?
And so when you say knowledge of it, like, I mean, is it basic or is it in depth that you have to show? For Rice's theorem.
Well, you have to do the various following things. You have to be able to state Rice's theorem. You need to be able to apply Rice's theorem to some language. Maybe you have to prove Rice's theorem, or probably more likely, I'll think of some way of making you change, right? Maybe it would be slightly different. So a specific language, but it's slightly different, and you'll have to do, we've done a whole lot of reductions. So on assignment 4, which I had to get down to making, there's going to be some reductions there. All right, and then on the test, there'll be some reductions. Yes?
Can you give something where you can't use Rice's theorem? What would you do then?
Well, if the input isn't a Turing machine, but the input is a Turing machine and a happy face, then Rice's theorem doesn't apply. All right? But any other questions about Rice's theorem? Yes. You weren't here for most of it.
Yeah.
What's your question?
Do we eat it?
Do we eat it?
Yeah.
Good question. It's good with Chinese and Japanese food.
Okay.
All right. So